it's just that went on the and like I think yeah, I'm thinking about very amazing.
Okay, let's start. Any questions about the homework? Who's done? Everyone finished? Couple of people, good. That's good progress. And I bet that everyone online finished as well, right? No, I mean, I'm happy that people are getting more efficient with this, because yeah, it's really not that hard. But today, I mean, first of all, we don't have that much left, right? Much time left. So we have next week essentially to finish our course material, and then Tuesday after we will have a final review, right? And people are asking online, what is the scope of the final exam? The scope is the entire course, right? So everything from the beginning to the end, but the emphasis will be on the second part, obviously, right? Okay, so today is yet another very exciting lecture because again, it's very unlikely that you will program a machine which has a single CPU in your life, right? So maybe if you're working in embedded domain, but even embedded systems these days have multiple CPUs. The question is, how does it work? So how does a system with multiple CPUs even works, right? And how does it access memory? And what does it mean for you as a developer, right? And I know that all of you probably used locks or other synchronization primitives in your life in the past, right? But the question is, like, do you really understand them? So we're gonna figure it out today. Okay, so just to start, so let's quickly figure out how x86 starts other CPUs, right? So everything up until now was happening on a single CPU. And I wasn't lying. So everything what we were covering was booting on this very first CPU. Remember when I was talking about the boot, I said that there is a funky protocol and the BIOS leaves the system in such a state that one CPU is assigned as a bootstrap CPU, and everything else, all other CPUs are waiting in some suspended state. And they're waiting for a special interrupt from this first CPU. And we will see how the x86 sends this interrupt, right? So, okay, cool. So again, at the very end of main here, again, main, which runs on the very first CPU, which we were like covering all this time, there will be this function, which called start others. And this function essentially starts other CPUs in the system, right? So physically, those CPUs, they're running, right? So BIOS was running on them, microcode was loading, caches were initialized, so a lot had happened, but they're kind of like suspended, right? And I mean, security researchers obviously, they do study what is happening, how those CPUs are initialized, but for us, it doesn't matter. We just say, okay, they're somehow suspended. So the start other CPUs follows the following protocol. So first of all, each of these CPUs will start in this real mode of execution, right? So we need again to bootstrap the CPU into like enable segmentation, enable paging, stuff like that, right? So we need some kind of a start code to run on those CPUs, right? And remember, when BIOS was starting this very first CPU, it started from the bootloader. Bootloader was loaded from the disk into like address 7C00, and BIOS jumped into it, and that code which we control initialized the machine. So we do something similar here. We say, okay, let's have an assembly sequence which we carefully craft, and we put it in some well-known location, which we can advertise to other CPUs, right? And x86 chooses 7000. And it's semi-random. It just the x86 knows that physical memory at this address is available. It's highly unlikely that the system has less. If yes, then you probably cannot do anything anyway. And second, it's not used by anything else, right? Okay. And then we will pass certain parameters, certain arguments to other CPUs by essentially like configuring, passing this information in well-known locations. So let's take a look at how it's done. So again, a similar trick to how we created the very first process in the system. So we have a small assembly sequence included in the kernel. And it's like the linker created those labels, binary entry other start and binary entry other sites for us, right? So we move this assembly into the physical address of 7C00. Since we cannot access the physical address, we need to do P2V because we say, look, we only can access a virtual address. And so there is this page, but yeah, so it will be essentially shifted by 2 GB, right? And this is where we copy this initial sequence, right? And after that, we say, look, we will be running in a loop. Like we somehow know how many CPUs we're starting, right? So again, there are multiple ways to figure it out. I think x86 just statically says, okay, when you compile it, you say, I'm gonna support 2 CPUs, right? For each of these new CPUs, you're gonna allocate a stack, right? And I will ask you, like, we haven't done a poll in a while, but today is the day again. So let's go on to this address and try to answer the question, what will be running on this stack? So literally, why do we need a stack? Let me quickly enable this activity. Happily not running, but just give me a sec. No, really? Yeah. All everywhere, our program of choice doesn't start from the first time always, but it's okay, we can start it from the second time. Okay, so I enable it. And I will actually probably present for a second. Do you see it? Yeah, some people are answering. How do we? Let me exit from here, since everyone there in Linux as well. So can I pause it? I have to actually exit. Just wanted to discuss the results. So what do we have here? So does anyone remember how to enable? There was an option of presenting from poll anywhere, right? But give me do this, no? Okay, those are our. Okay, so what do we think will be running there? So 12 in the new CPU. Who believes that it will be for the cell in this class? No, just online. Okay. Scheduler in the new CPU. That's good. So who believes that it's scheduler? One person? Wow, a couple of people. Okay, then what are the versions? So what do you think will be running there? Don't be shy.
This is the first option.
Shell in the new CPU. Init process.
Yeah.
Everyone believes that it's running here. Okay. So why do you think it will be running init? Okay, I'll ask you a different question. What is in it, like conceptually?
It's a loop that keeps restarting.
Correct. It's just the loop which keeps restarting the cell. So why do we need another loop which will restart the cell? Me neither. I don't know, right? So do we need two cells upon boot? So probably not in it, and we don't need a cell either, right? So, but what is the meaningful option here? So we have multiple CPUs in the systems, right? I kind of briefly told you, like we want something to run on those new CPUs, right? What will be running on those CPUs permanently? And say again.
You should always have.
I agree. So I think that the scheduler, we need to run the scheduler, meaning because maybe the system is not running any processes, right? So then probably it's time to exit, right? Because it's not clear how to create new ones. But roughly speaking, we have one init starts shell pops up on a screen. We see it, we can type commands, create new processes, right? And the schedulers on each CPU will pick up those processes and will try running them. To do that, the scheduler itself needs to run, right? So run this infinite loop, like saying, okay, yeah, I'll look at the process queue, like process array in x86, and I see which processes are in runnable state, and I will try to schedule something, right? So I agree. So it's not super clear right away from this, from my exposition yet, but we will get to that in a second. So the correct answer is yes, scheduler on the new CPU, right? I just wanted to make sure that we understand it because we don't need an init. One init is enough. It will start a cell will show up on a screen, right? Okay, fix your answer if you're following what we're doing here. And everyone is good? Some people are still actively fixing. So, remember the answer, next process which x86 create on the new CPU will have its own kernel stack because each process will have its own kernel stack. So it can process interrupts and stuff like that, right? Actually, I forgot you to tell why we need this stack. Probably we should come back to it at some point because it's also important. But anyway, so okay, so we got the point. So we need a new stack. And this new stack will be, in the end, will be running scheduler, right? So we allocate it here, and we say, look, we will advertise it to the other CPUs. So essentially, how can we send this information to the CPU which haven't yet booted, right? So we say, look, we're gonna use a well-known memory location, and what we specifically do here. So if we chose to put the code at 7C00, we will put arguments which we're passing to the other CPUs just right below it. So 7C00 -4, -8, -12, right? So it's just like three integer arguments in memory. Is that clear? So specifically, we say, look, we're gonna advertise our stack. We will advertise the entry point, like of the kernel, the function which we want the CPU to run. And we will advertise a page table which the CPU can use while booting, right? And we're gonna reuse this. Remember the old entry page directory. It's a 4 megabyte page table, so it has one level and only 2 entries, right? But that's enough for us to boot. Question?
Yeah. So at the beginning, we have a code for some virtual address. Then we use the man move code that inside the function, will the code goes to the page table?
Inside the function move?
Yeah, and the code is the virtual address. Will this address translate through the page table?
Okay, that's a great question. So who can tell me?
Probably we should look at what's inside the menu.
We can take a look at what it's move. That's a good idea too. I mean, I get it. So maybe it's not obvious. Hold on.
Yeah. Very.
No, look, it's let's get there. We have time. X with 6. I cannot build it on my Mac, so I quickly will go into CADE. Mm. Mm. I have it quickly. Let's quickly build. We can do something like opt dump of the disassemble of the kernel, pipe it to less, mem move. Let's look for something like mem move something like this. So this is implementation of the mem move function, right? So if we like it's assembly, so let me first show you quickly. I put it in the background, so I will actually don't really remember where the mem move is implemented. So let me quickly grab for it. So I have probably a ton of options. Maybe something like util. Not the best way to search, but okay. Move main. So probably here. So memmove itself is a very simple, like again, in a real system, memmove will be optimized slightly more, but that's good enough. So memmove essentially takes two memory locations and implements a loop, right? It's clear to everyone, right? So it's the C code for memmove, right? Where we're just copying memory from one address to another. And specific copy happens, let's say, in this string where we say, so we have two pointers and we're just accessing them and like copying one from another, right? And or here as well, right? Get it? So if I quit this and I go back to the implementation and assembly, we have this function. And again, since we already had a midterm and I was asking, I think I was asking something about memmove, I'm not exactly sure, but or memcpi, which is very similar. But in the end, everything boils down to some kind of an instruction which is similar, I would say, to something like this, right? So well, cannot immediately guess which instruction is doing the actual copy, but it will be a memory move instruction, right? At this point, you ask a question, so does it go through the page table? So what do you think? Right. So what your classmate is saying, okay, cool. Yeah. So any memory operation will go through a page table because the page tables are enabled, right? So do you agree with this?
Yeah.
Does everyone agree?
Yeah.
Are we clear that this works? Like what I was trying to show here is that every time you have a question like that, you should kind of say, okay, I kind of understand what's going on underneath. I know what's inside the memmove because I've seen it before. Even in Linux, you can go into libc. It's a pile of a lot of code and with a lot of if-def, so it will be a little harder to find. But you can with like even GitHub will help you with go to definition, and you will find the definition of memmove in libc, right? So and then internally there will be a move instruction which does it, and then you say like, what about page tables? Yes, so both segmentation and paging are enabled, right? So every operation will go through this, right? So it shouldn't be a miracle to you. So like you simply cannot access the physical address, right? So if I switch back to the lecture here, let me actually disable this. I will ask back. So what prompted the question? Why were you confused about it? Because I said that I'm gonna use a physical address here.
Yeah, but we don't first this does not translate through the page table. This is the computer. Second one is the available memory space for us?
Say again.
I mean, whether it's available. I mean, I mean, available or not, I mean, before we use, we should allocate, right? Did we allocate that?
Okay, hold on. So, okay, you're saying the following. You're saying before using memory, you should allocate it, right?
Yeah.
Well, that's a nice belief. Everyone who goes to computer science program in any college says, I should allocate memory before using it, right? But
Yeah.
people who build operating systems don't believe in it. They know that they can use any memory. They don't care. Why? Because they know how CPU works underneath. They say, okay, we are gods. We boot into the machine and create everything else, right? Which means that we control what we do with memory. And in most cases, they will try to allocate. But if they know for sure that if this is the chunk of memory, maybe allocator running on this memory, but this area is never used by anything else because we created it, right, this way. We are free to do whatever we wanted with this memory. So like you should understand it, like it's like a stack. So the stack is nothing, it's given to you by the compiler. But if you know what you're doing, you can reset the stack pointer in almost any language, or in any language which allows unsafe operations, which means allows you to access registers, right? So Python, for example, it's hard in Python, but you can implement a C function link against Python and then or assembly function and then reset the stack, right? So if you know what you're doing, you can do it, right? Because you know how machine works, right? And that's the point of my class, essentially, to teach you how machine works. So I claim that this address is not used for anything. It's not on the allocator's free mem list. Why is that? Because I said that allocator will be initialized from the end symbol and up, right? And this is end is higher than 7000, right? So I just create the world this way, right? So I construct it.
It's easy, page table.
Is it in the page table?
Yeah, the page table.
Good question. Okay, great question. So did we map this address? Is it in a page table?
Yeah.
This address.
When we map it.
Hold on.
Why?
Wait, hold on. Virtual address. Is this virtual address mapped? Can we access this virtual address?
Probably not.
Correct. We cannot access this virtual address, right? I agree with this. But we can access the address, this physical address, because we mapped it at 7C00 plus 2 GBs, right? I mean, this is a great discussion because look, do you remember how we constructed the address space? I'm just finding this free space. So our physical memory from address 0 to fistop is mapped with a shift, right, to 2 GBs to 2 GBs plus fistop, right? Agree with this? And the physical address 7000 is sitting here, right? We cannot access it directly. So if we issue a virtual address, which is 7000, it's not in a page table, right? So we immediately get a page fault, right? Because we don't have an entry for this. That's why we say, okay, we will use P2V of it, which essentially gives us 7000 plus 2 GBs, right? And we land somewhere here. And
what's the value of fistop?
What's the value of fistop? I think it's roughly 238. It's a constant 238 megabytes. It's configured at compile time, and this is the max physical memory which x86 supports, right? Agree? Question.
Let me ask this. How much overhead would it be to just switch off paging per second?
So it's a pretty fault.
Hold on. Yeah, so first of all, you probably can switch off paging, but it's not trivial because your instruction pointer sits somewhere here. And you first have to like jump to some lower addresses. So have to some kind of like a proxy code here, right? You can do this if you want. It's a little exotic and people probably will yell at you, but in theory it's possible, right? So
if you have page fault,
if you just disable paging, yeah, there will be a page fault.
so here is a page fault.
Wait, hold on. What? Why? We are not accessing 7C00, right?
Yeah.
We're accessing P2V, which will give us 7C00.
Plus 2 GB.
Yeah, plus 2 GB.
So this address said this range should be mapped before, right?
Yeah. And we mapped it. Remember when we created the kernel page table on which we're currently running the main function, it maps those addresses, right? So it maps all available physical memory to FISTOP with a 2 GB shift. That's how we did it, right? Okay, but I will ask you a slightly different question, even trickier.
Wait a minute. So here, probably, yeah, you ask first.
Yeah. Okay. So I ask first. So here, when we send this magical interrupt, we actually convert this address back to physical. Why do we do this? Remember, this interrupt will be sent to other CPUs. And we're passing this bit of information to these other CPUs. That's actually the hardware interface allows you to send one integer. And this is the integer which we're sending. Well, almost.
It's shared by every CPU.
It's shared by every CPU, but why are we sending a physical address, not virtual?
If that agent isn't enabled on that CPU?
Correct. So these CPUs, like we're running on the very first CPUs which booted, which was Bootstrap BSP, Bootstrap CPU, and those application processors are still sitting in real mode. So they only understand physical addresses right now. That's why we chose this physical address in low range of addresses, right? Because the physical memory at the higher range might not be available, right? Or might be used for something else. And we're sending this physical address to to all other CPUs in the loop, right? Agree? So is it clear now what's going on? I mean, again, I agree that it's unusual when you look at it for the first time. And it's also unusual because in every class, probably it's very rare that someone will tell you in a class on C++ or C# that you're gonna access a memory bypassing memory allocator. In practice, it's done, but rarely, right? So only to implement funky features like language runtimes, like asynchronous runtimes, like async features in Rust, for example. You know, C++ also has async, I believe, right? So it's like coroutines or something.
So basically, since 7,000 x 7,000 is the same thing as bootloader, immediately all it does is set up segmentation and paging. So
Yeah, we're gonna take a look in a second. Yeah.
Okay.
So let's take a look at what this init code entry other is doing. So, okay, so we send it, advertise it to other CPUs with this magical interrupt. Again, it goes through this. Remember, your homework tells you to initialize local advanced programmable interrupt controller. So this is the machinery underneath which does it. And this is the entry other. So this is the code which starts on another CPU. Again, since we're in real mode, we generate 16-bit instructions. We immediately disable the interrupts just in case, because we don't really know how to handle them. We reset all the segment registers to zeros. It's pretty much the same sequence which you've seen before. So it's similar to how you booted on the first CPU, but a little bit simplified. So again, you enable paging here, or what is that you're doing? Enable protection mode, long jump to make sure that like very similar to your homework 3, in which you long jump to this label to essentially reloaded the global descriptor table. Then now we are ready to, we loaded it here actually, by the way, reset the segments to like for kernel code, kernel data here. So everything like looks familiar at this point because we did it a couple of times. And then we go through like familiar steps. We say, okay, since we're going to be using a 4 megabyte page table, just for simplicity, we will set on this 4 megabyte extension. We load the entry page directory into the CR3, and remember it was passed at like, since start is compiled to be 7000, and we passed everything below that. So it's start minus 12. This is where we place this argument on another CPU. We enable paging and essentially say, look, everything is good now. We'll set some stack. Again, stack was passed as an argument, and the entry point was passed as an argument to us as well. And we just call into the C function. And at this point, we running this other function, which is called on another CPU. We're not going to start with main because main did some initialization, which is not necessary here. We start running with mp-enter. Here we say, look, let's initialize a normal page table because we don't want to run for too long on this entry page directory. Initialize segmentation. Here's like a bit of trick here because, by the way, each CPU will have its own global descriptor table, right? A good point for a poll, but we'll skip it. So I'll ask you a question. So why do we need a private global descriptor table? So C, this variable C, there is an array of CPUs which x86 defines. It uses a function, CPU ID, which talks to the hardware, and hardware returns the ID of a CPU. On physical CPU 0, it will return 0. On physical CPU 1, it will return 1, right? And then it has an array of CPUs, and it returns an entry in this array. And so each entry in the array has its own global descriptor table. It seems that no matter on which CPU you're running, right, the entries in the global descriptor table, at least here, look the same, right? But there will be a different entry. So which entry, why do we need a different global descriptor table? Hint here is that at least one entry will be different.
Stack.
Which stack?
Kernels.
Correct.
Yeah.
So do we understand this? Because look, all physical CPUs will be running processes concurrently. At any moment of time, any of these processes can get an interrupt. Maybe it will be executing a syscall. In order to execute a syscall, they will execute an int, what is that? Int 64 instruction, right? They enter this, the process enters the kernel. And the moment it enters the kernel, it needs a kernel stack, right? This kernel stack is pointed by the TSS, right? And so, which means that we need an entry in global descriptor table, a different TSS, which points to a different kernel stack. That's why we cannot use a single global descriptor table. And each physical CPU will have its own, right?
Yeah.
Is that clear? Okay. Okay, cool. So we initialize global descriptor table. So, and other, like, there will be some other per CPU variables, and like, it's not uncommon that CPUs have some private information, right? So the CPU structure has don't get surprised. We just talked about context switching. So when you context switch, each CPU runs a scheduler, and this is the pointer where the context of the scheduler is saved. It has its own TSS, and since global descriptor table points to the TSS, it's also a private variable to a CPU, right? And it has a current process which is currently running on this CPU. And like those two variables are used for disabling interrupts recursively. We're going to talk about it today or next week on Tuesday. Okay, got it. So physical CPUs might have some private variables, right? In a typical language, you will never see, you will see only thread local variables. The idea is similar. It's just that CPUs never exposed at the level of a language, or typically not exposed, right? So, but here we deal with physical hardware, so it's somewhat similar idea. So it's like thread local, but CPU local, right? Okay, cool, but we understood it, I hope, right? So at this point, like at the end of this MP entry, you enter the function MP main. It prints a string saying, okay, CPU is running, right? And you say, enable the interrupts, set the flag that CPU has started, and enter the scheduler, right? So each CPU, each physical CPU ends with entering the scheduler, like we talked last time, and the scheduler will be running this infinite loop, trying to look at the array of processes in a system, pick a process which is ready to run, and switch to it and run it, right? And physically, concurrently, if you have a machine with multiple CPUs, multiple processes will be running physically on those different CPUs, right? Is that clear? Question?
Maybe you just answered it, but why do you need to on the other CPUs that you yourself sort of?
I forgot exactly. So maybe grab for this variable and see how it's used in x86. I don't remember, but it shouldn't be something hard. But again, so we got to the point where we have a system which runs multiple physical CPUs. To be honest, the bootstrap sequence is not even that hard. So it seems intuitive, like send some magical interrupt, then it boots, right? So, well, you have to configure the interrupt controller, but with a little bit of reading, we can probably do it, right? So, but we live in this idea where we kind of like, we're comfortable with this idea that multiple physical CPUs are running, right? Our next question, which is a little bit tricky, is what happens underneath? Because there is one physical memory, right? So CPUs are physically different. They have like pipelines and stuff like that, instruction pointers, but there is one single memory, right? So, and I mean, it was covered in other classes, but let's go over it again. So who can tell me how do we access memory from multiple CPUs? What's the most important piece of technology which enables this? Or a protocol name?
There's a main bus.
Correct. And this bus implements a protocol which is called cache coherence, meaning that there is a specific protocol implemented by hardware which somehow guarantees that when you access the memory from multiple CPUs at the same physical time, one CPU will probably be chosen as a winner. Otherwise, it doesn't make sense, although those architectures did exist, where two CPUs try to write or read the same region of memory, and then you define the results of your computation become undefined at this point, right? So, or it's hard to program. Right, so let me just kind of like review how it works. So again, on laptop grade CPUs, we have one physical processor, right? So if you open up your CPU, you will see one piece of silicon, right? So you will not see it; it will be all wrapped in plastic. But if you're like really careful with willing to file it, you will see it eventually, right? So which is fun. So each of these processes have something what is called the core. So really core has registers like a pipeline, which talks to those registers like actual logic elements like private L1 data and L1 instruction caches. And like meaning that those are separated like instruction and data caches, but L2 is shared between instructions and data. And that's the core. On Intel, like so, organization of a core can be different between different CPU architectures, but this one is pretty common, right? So, and you say when I have a multi-core CPU, right? So then it means that my laptop, it actually one piece of silicon has multiple cores. They are built next to each other and they can talk to each other, but they're sitting on that one piece of silicon, right? So, and the cores are kind of identical almost, right? That not a surprise, right? So, and on the same piece of die, same piece of silicon, there will be a shared L3 cache, right? So it's shared between all the cores, and it will have connections to like a memory controller, PCI bus, and something what is called quick path interconnect. It's a cross socket link. I will explain in a second, but we'll see. So, and this thing, when you go to like, if you have a desktop CPU and you want to upgrade it, so you go to the store, you buy specifically this piece, right? So, but maybe it will have like 16 cores today, right? Agree? So not super hard. Okay, and then of course, memory controller is connected to DRAM banks. In practice, Intel actually has multiple memory controllers, I think 2 on a modern architecture, and those connections are called channels. They have like limited bandwidth in practice again, and Intel has 3 for each memory controller, so a total of 6 channels. Again, come back to advanced operating systems, I will explain the bandwidth equation for those, for those channels. Why it matters, because there are workloads like memcpy, which can actually saturate this link. Like you literally hit the limit of this link, and you can only process data with the speed at which you can pump data from memory. Like that becomes your bottleneck, right? Which is a little surprising, right? Because you never think about it this way. So PCI bus connects to like PCI devices, like it's my PCI-based attached solid-state drive, what is like commonly known as NVMe, non-volatile memory on PCI bus. And this QPI link, or quick path interconnect, is a cross-socket link, which if you buy a server machine, which comes with multiple physical processors, this implements a connection between the processors, right? So I probably talked about it in my earlier lectures, and the other processor will have the same architecture. What's funky about it is that it will have its own memory controllers, which will be connected locally to DRAM banks. And as we see in a second, like you can guess it kind of, that the latency of accessing this memory is lower than latency of going through this link and accessing this remote memory, right? That's why we call those machines and non-uniform memory architectures, or NUMA, right? And if you are in this world of like programming something very efficient or very low latency, let's say high frequency trading, then this becomes, it matters to you. Like again, languages, there are APIs which expose this location of memory, but probably none of you actually played with it yet, right? But it's there in practice. Latencies are different, right? And not surprisingly, accessing your local PCI devices is a little faster than accessing remote PCI devices, right? Funky. So actually, you open up the physical blade server, which you pull out of a rack, and it will have like it's a distributed system, although you never think about it this way, right? But really, it's a distributed system, and it becomes more and more distributed today because people sometimes place those memories even on different in different racks. So something what is called disaggregated memory, right? So this links between this link can be so fast that it can allows you to place the memory not on on the same system board, but place it in a different rack, right? But again, don't be surprised. So you will see more of it in the future, right? Okay, so this is nice distributed system, right? x86 booted, runs on all of these cores, for example. Now let's see what happens.
The typo should be processor 1, 0, 1.
Yeah, should be a typo. I probably just copy pasted. Sorry. Okay, how do we access memory? So imagine we're running something on this processor 0, core 1. The latency of accessing register, I'd say 0 cycles, so you can access the register within the same cycle in a pipeline, right? In most cases. And imagine you're loading an address, right? So you're loading an address, and typically the machine will check, okay, is it in first level cache? Well, let's assume the answer is no. It's in the second level cache. Wow, let's assume the answer is no. This memory location was never accessed or was evicted from the cache. You go to the last level cache, it says no, but it knows where in DRAM this cache line should be stored. And it sends a request to DRAM. DRAM says, okay, yes, I do have a cache line. This memory, physical memory is present, right? And then you're essentially typically, again, it varies slightly, but in my diagram, I actually populated all the caches with this cache line. It was true 5 years ago, and maybe today, this will not happen because you're wasting too much memory, and it's called inclusive versus exclusive caches, but it doesn't matter for our today's discussion. So maybe it will not happen, and maybe it will change again in the future, right? But fine. So, but we got the idea. The cache line is brought into the caching hierarchy. So obviously, the next load, if you access it again from the cache, from the same cache, will give you this line immediately, right? Agree with this? With a latency of let's say 3 to 4 cycles, according to Agner Fog, or we can do our measurement ourselves, right? But we're smart, we know how long it takes.
So if different processor has its own memory controller, where could they get the global information about the where the memory or cache line allocate.
Right, so it's typically here in a last level cache, there is something what is called cache engagement. I forgot exactly. So it's part of the architecture class, but typically last level cache keep tracks of where how the physical address is mapped to DRAM banks, and mappings actually can be different as well. And BIOS, in some funky BIOSes on server grade machines, you can choose the mapping policy. Sometimes it matters as well.
So every time we do any operation, the memory, it will have some kind of like synchronize across all the processors.
Right. And again, I don't I kind of talk about a very simple version of it, but there will be many details underneath. So okay, let's move forward. So let's say what if we load the cache line on this core, same cache line. So again, kind of same happens. You say, look, I will check my local cache, L1, check my private L2. The cache line is not there, so we're gonna go to L3, but L3 is happy here and says, okay, I actually have this cache line here, so I will give it back to you. Since I have the valid copy, like it's the most recent copy of this cache line, right? So I'll give it right to you. And that will save you some time because access to the last level cache is, we'll talk in a second, but roughly like 50 cycles, right? Okay, so the question is now, what happens when we write a cache line, right? So this is where we need to arbitrate and do the, essentially choose who is the winner and how you write, right? Okay, so let's imagine this guy does a store into this cache line, right? It says, okay, I will try to access this cache line on the write, and it's there in a cache. But the problem is that the same cache line exists on other CPUs. And this is where this protocol cache coherent kicks in. So naively, you say, look, there will be only single writer. Like imagine you, I don't know, selling flowers in Red Butte Garden, you have multiple counters, you have a list of, inventory. And when someone checks out, says, okay, you have a pine tree. And they say, let me get this list and I will mark how many pine trees I have, right? In the physical world, you will be passing this document between multiple, checkouts, right? To make sure that you have a consistent copy. Otherwise, you oversell, right? And then we'll deal with refunds. Do we agree on this? So the same kind of protocol is implemented here. So it will be concurrent readers because we allow concurrent read-only cache lines, but a single writer. So concurrent readers, what is it? Crew. Concurrent readers, exclusive writers, right? So, okay, how to achieve exclusivity? So the protocol plays like this. It goes down the caching hierarchy, down to the last level cache. Last level cache keeps track of who has the copy of the same cache line. And this last level cache essentially sends invalidation requests to everyone who has it. And it's like core one in this example says, okay, look, you have it, so please no longer use it, right? And at this point, this core receives an acknowledgement that it has an exclusive access to this cache line, right? The protocol actually tracks the states of those cache lines, right? And you've seen those names. So the protocol is called something like MESI, which stands for the state. So modified, exclusive, shared, invalid, right? So the state of the cache line, right? So at this point, you can both read and write on this core. Agree with this? And if you want to read it again, then what happens? Does anyone know? Does anyone know the protocol?
Right.
Different core. So
You will need to go down to the memory.
you will need to go down to memory. Do you have an idea? It's something what is called a write back. So again, the protocols can vary in the implementation, but roughly speaking, to be consistent, it says, okay, look, I will check my caches, go to last level cache. Last level cache keeps track of where the cache line is, goes up, says, okay, someone wants to read it. And at this point, you can say, look, maybe this cache line can be changed in a shared state and sent here. And that's a possibility, but modern, at least Intel does something what is known as write back, and it sends this cache line back to memory. It just simplifies the development of the protocol, and again gives this cache line, it's, let's say, in a shared state to this core, right? Write back. like the actual action of writing back to memory is called a write back. Write through is, I think, relates to how you configure the caches, whether when you do a write in the first place here, in my example, the cache line was retained here, but write through would push this cache line immediately to the memory, which slows you down. But if you talk to, like, for example, a device over PCI bus, you want to do this. But again, let's not get into those details, right? So, but okay, so is this idea clear? So that's how we input, that's how the machine works underneath. So there's cache lines. Everything is in terms of cache lines. Does anyone know the size of the cache line on Intel? The size is the same for each level.
Okay, 64.
64 is correct. What is the unit?
Kilobyte.
Kilobyte. That's a huge cache line. What if you're only writing a byte? You're gonna moving 64 kilobytes up and down. By the way, these caches are only 32 kilobytes. Just a hint. So must be
64 bytes.
64 bytes, correct. So again, you can choose a different cache line size. Who chooses and AMD and ARM chooses 64 bytes. Again, they ran a bunch of measurements and said, okay, that's an optimal size, right? For whatever workloads, may not be always optimal, right? Okay, so we got it. So everything in terms of cache lines. So it's like units of physical memory which are bounced between the cores. If this core tries to write something, it will play the same protocol, but across this link between them, right? So the memory, in the end, it looks like the memory is a single thing, because if you want to write, you will try to you will request for ownership, send a request for ownership, and maybe you will win this. And if there are multiple cores trying to write the same cache line, the last level cache will arbitrate and choose one core and then choose another next time, right? Right? But only one writer will exist in a single moment in time. Right. What you're asking, or what you're talking about, is that you're saying someone has to keep track of where the cache line is, right? And yes, last level cache does it on Intel. And again, there are multiple protocols. There are protocols which are called snooping based, and then everyone is notified about this action, and no one keeps track of where stuff is. They don't scale very well because they compete for resources on a bus. But directory-based protocols are kind of like a network, like a real distributed protocol. You send a message on a memory bus to the directory. Directory literally for each cache line will keep its state, and like if it's in a shared state, will keep all the core IDs, CPU ID like core 0 and maybe 5 and 7, and will know like who owns the cache line. And again, like differences in those protocols, they change fast enough that I don't keep track. Every time I have to go back to those, like when it matters to me, I have to read about them. Then it explodes your mind very easily. So it's tricky.
Are these protocols typically in some embedded chip somewhere, or is it the responsibility of the operating system?
No. It's in hardware. Those protocols are implemented by Intel. Intel releases certain details of those protocols, but not full details. Gotcha. And they are implemented physically by logic of the last level cache and other parts of the die, right?
So this just should all be physical just, right?
Yeah. So cache lines are addressed, by physical addresses. And there are reasons for doing this. Again, take an architecture class, but you will understand. All good? Everyone is clear? Okay, cool. So with this in mind, let's just a couple of interesting details. So again, your job interview at a big 5 companies or something like that, or a small startup, and now they ask you like, how long it takes you to access an individual parts of this memory hierarchy. Let's just quickly go through it. So first level cache is roughly 4 cycles. And the size of the cache is like 32 kilobytes for data and 32 kilobytes for instructions, right? Who can tell me the number for the second level cache?
64.
64.
No, 128.
Wait, size or latency? Let's do latency first. 10. Okay, like agree. And the size? It's nice to have a feel because
32 megabyte.
no, this one is 32 megabyte, 32 megabytes. A little lower because I mean, the trade-off obviously, the larger the cache, the more logic, like more gates, the longer it takes to access the cache, right? So that's why the
But the
like
size
faster
will be-
caches are smaller.
It's still limited, 64. 122, 128.
Okay. It's a little bit interesting. So Intel typically comes with 1 megabyte of L2 cache, which is a huge cache, right? So because remember, I keep sharing this anecdote that the first desktop which I had at home was 16 megabytes DRAM, and this one megabyte cache, like you can boot x86 in this 1 megabyte. I mean, of course it loads itself above the first megabyte, but like if you're very, very careful, you can design it differently. Okay, so roughly speaking, on this machine, like it's still 256 kilobytes, but on modern machines, it bumped up to 1 megabyte, right, per core. So which means that like if you have 4 cores, you will have 4 megabytes of L1 cache total in a system, right? So what about L3? This last level cache, latency and size. 32 megabytes.
128 megabyte.
No, 32 megabytes is a good number. And what's the latency you're thinking? Yeah, roughly 50. And again, on this machine, like I got the number from a specific paper. It was 53 cycles, 30 megabytes. But roughly the equation today, again, first of all, this cache is no longer like a single big cache. It consists of multiple banks. And it's typically, the equation is that it's 1 megabyte per core. So this is 1 megabyte, but private per core. And this is 1 megabyte of a shared last level cache. So if you have a 32 core machine, then it will be 32 megabytes. On a 20 core Intel, it will be like 20 megabytes typically, right? Again, worth knowing. Why? Because you say, look, I build a file system. It has to be very, very fast. You can optimize the file system in such a manner that metadata about where the blocks on disk are all fit in this last level cache or something like that. It matters when you go into the algorithms class and start thinking about, okay, I want some metadata for this algorithm to sit in like in a cache and just only like, so I never touch the disk on a critical pass and I only read the data from disk, right? So it matters. So in a modern world, it surprisingly matters. Okay, so latency of accessing memory, who can tell me? Yeah, and what is the size? If you go to the Dell website, how big of a, like again, machine with how much memory you can buy? A lot. Right. So it changes with every year, right? So roughly on this machine, it was 241 cycles. Dell sells you a motherboard with 96 memory slots. And back then, the max DRAM was 128. So it's right, 128 megabytes by 96. That will be your number. So it puts you in like tens of terabytes, right? So that's not bad. So today, probably this number is even more. Again, why it matters to you? Someone says, okay, we have a huge data set, big data, right? Let's buy Amazon credits and run something on Amazon because we will not fit in the memory of a single machine. Pay for Amazon or for whatever other cloud you like. Sometimes maybe the equation will work in such a manner that paying once for this beefy machine with a tens of terabytes of memory might play into your favor, right? So again, it's not always true, but just be aware of the fact that it can be the case, right? And as a systems designer, and again, you simply program some language, Python, simple homework, everything is less than 96 kilobytes, right? But in a real world, you might see workloads which are giant. So for example, we work with like genomes, they half a terabyte easy. Again, how long does it even take you to read half a terabyte from memory into the CPUs, right? To even like touch every bit of it, for example, right? So it becomes important. Okay, any questions about it? All good? Just a couple of other numbers. Don't get surprised that going up the hierarchy will take you time because you have to go through the last level cache and up. Like if the line is there, so it's 132 cycles, so kind of like still faster than accessing memory, but only like by half, right? And obviously, if you go to a last level cache of another core, like maybe the cache line was there last time and you will fetch it from there, it actually takes you 215 cycles, so this number. And that's kind of scary because it's literally like accessing your local memory is the same speed as accessing the remote last level cache, right? Over this link, just because it takes time to cross this link. So again, it matters. I've seen workloads in which like this matters a lot. Obviously, remote memory is a little further away, as I was mentioning, and obviously, if you go up the levels of this hierarchy, you will pay even more cycles, right? So it's like, again, it's a distributed system, so it's not like everything is immediately fast and available to you. Okay, so we got the point. So we did this detour of Intel memory hierarchy, so we understand the latencies, roughly speaking. We know how the cache lines are bounced between the cores. And now we arrive to this topic of synchronization. So roughly speaking, why do we need locks to begin with, right? So let me illustrate it with an example. And the minimal example, which I was able to come up with, imagine you have something like a disk driver, and maybe each process in the system through a file system adds requests to a queue, which we implement as a linked list. You say, I want to write something from disk, but maybe the driver can write one request at a time. So you add to a queue, right, to the list. And the list we will implement with a very simple data structure, maybe even simpler than we do in homework. So it just has a piece of data. Each element of the list will have in this specific example, just like an integer of data and a pointer to the next element, right? So you literally have a head of the list, some global variable, which points to the beginning, right? Initially it's 0. When you insert, you allocate a new element, right? Imagine you have a memory allocator like malloc, luxury in x86 doesn't exist, but maybe where we build it because we want it. And then you essentially say, okay, look, I will assign the data which is passed here to this element. We'll essentially do patch the next pointer and patch the local variable. So that's your insertion, right? Very, very simple, right? So, okay, cool. So now let's imagine something is running on these two CPUs and both of them are running a process, each one of them running a process, and each of these processes try to write something to the disk. So the goes something like that. So you have two CPUs, one linked list, one global variable. Let's imagine CPU 1 tries to insert something. It locally talks to malloc, allocates an element. Then CPU 2 at around the same time talks to malloc, allocates an element. They both write their data elements into this list. They arrive to this line which says L next equals to the list. They read this list variable. Why is it possible? Because it's a global variable. So the cache line will be in a read-only state on one CPU, and the same cache line will be in a read-only state on another CPU. Agree with this? We just went through the protocol, so why not? We're reading this variable, right? So this is the read load. Right, so that's totally fine. And L, the cache line which contains the L, it's writable here, and it's cache line A. And obviously, the cache line which contains this L, right, because we allocated it here, will be writable here, but it's a different cache line. So they both can write at the same time. Agree with this again? Okay, cool. And this point, we say, look, sure, one of them says, okay, I want to write into this global list variable, right? So, and okay, remember the list was just read-only here and read-only on this CPU. So it will send, let's assume this CPU says, okay, I want to request ownership for this cache line. the caches will send invalidation requests saying, okay, you no longer own this. It will be in invalid state on this core, and you will have it from read-only upgraded to exclusive state, right? So you can write first, right? So this CPU does this assignment saying write into this global variable list, right? So everything is good. And at this point, this other CPU does the same. So implements this, tries to do this right. So remember, this cache line was in the invalid state on this CPU. It was in the exclusive, or then later when it was written, was in modified state on this CPU. So this goes to its local last level cache. Last level cache says, okay, please do the write back. And eventually this line is written to DRAM and is given to this one in an exclusive state, right? So same protocol, just mapped on those operations, right? And okay, so what actually went wrong? Let's do another poll. So, and we'll try to understand really what actually went wrong in this wonderful setup. So if anything went wrong, maybe nothing went wrong. And let me just try to context switch back. Where's my poll? Poll. We should play a game. If you access the poll website faster than I am, then you know you're the winners. Everyone gets full points. And I actually probably failing this game altogether. But I'm here, almost there. Okay, it's active now. So is everything okay with those insertions? Like, again, I will leave this picture for a second, so you understand what actually was happening, and then we'll discuss the results. On the left, CPU 2 is on the right. Let's wait for a sec for more requests, for more answers. Are you still watching? Are you still looking at the picture? Good. There is a couple of good answers, but not many. So we have 20% of people who say that the list pointer, the head pointer is corrupted. So anyone agrees with this? Is it corrupted? Well, probably according to if you want to be very rigorous about it, so it's not really, you have to define what corrupted means, right? But at least it points to some element, right? So maybe let's say it's not corrupted. We have also some people saying that the new element from CPU 2 is lost, but it seems to me that it's on the list right now. The pink pointer points to the green element, which was inserted from CPU 2. So it seems that this one is on the list, right? There is also one or a couple of people who say that it's a null pointer dereference, right? So, but clearly there are no null pointer dereferences here, right? So what went wrong here is that element on the CPU 1 is actually lost, right? Do we agree with this? So, and yeah, we all are right. So this element is sitting there in memory. We allocated it, but we will never be able to find it again, right? So you will traverse the list and it will never go, you will never find it. Question? Yeah, I closed it. Sorry. You will have to move fast. Yeah. I can reopen it for you, okay? Not that I'm mean, you know. Yeah. Like I reopened it. Not yet. I tried. Let's say I tried. Where is this nonsensical poll? It will take me like, oh man, it tells me to log in. That's probably, you know, invalidated, like 3-factor. Man, just give it back to me, people. Let me reopen it for you. Yeah, let's. It's so annoying. Okay, let me close this thing. No. No, really? Okay, let me end slideshow real quick. Actually, probably Control Z here again. Was trying to, yeah, to reopen the, like now it works, right? Okay, I reopened it for you for 2 seconds, but say again. Only one participant. No, it's probably because I reopened it and it's a new kind of thing. Okay.
We don't have to redo it.
Yeah, probably not. Hopefully not. If so, everyone will get credit. Don't worry. But I switch my slide deck. Okay, let's quickly go back here. Okay, let's finish this one. So this element is lost. We are all agree on that. That's cool, right? So okay, so obviously we need to fix it, but we see the problem, right? So if you write the linked list like this in a real system, it will fail, right? Agree? Okay. So how many people saw this in the previous classes? Who knows the explanation how to fix it? No, yeah, good. Well, maybe not enough. Some shy hands. Okay, let's go into the details again. Since we're like running on the machine, we know everything. Okay, we want to implement something what is called mutual exclusion, right? So the idea is that we want to have an option to make sure that some sequence of code is executed only by one CPU at a time. And if another CPU tries to execute the same code, that other CPU will have to wait. By the way, there are multiple ways to implement synchronization. I'm just talking about this specific flavor, right? So there is like lock-free synchronization. You can do different things, but let's just for a second bear with me. So at a high level, our idea is that we will implement something what is called the lock, and we will acquire a lock on each CPU and then execute this green lines, which we call a critical section, meaning that this will be our critical section, meaning that if one CPU succeeds in acquiring the lock and enters the code here, starts executing those lines, another CPU will be parked here waiting for this first CPU to release the lock here, right? Agree? And that will fix the list because then this lines will be atomic. And if you think, stare at them for a second, you will understand that the problem which we had in the past will not happen now, right? Only one of them essentially will be adding both of them can execute malloc concurrently. And maybe even this line can be placed outside of the critical section because you don't have to be atomic there. You can update your private data outside of a critical section, but actual update on the list will be atomic, right? Okay, so if I ask you a question, so how can we implement acquire? Do we know? Anyone ever build a spin lock?
Yeah.
Yeah, okay, tell us.
Probably it's based on the always hardware instruction like test and set stuff to see whether a variable change or not.
So you say you need a special hardware support, which is like some instruction which does test and set, but let's go one level up. What is conceptually should be inside this acquire code?
Kind of like track of a flag, whether a flag to.
We will have a flag for whether the lock, well, I cannot spell either, flag. Wow. And so it says taken or not, right? Taken or free. And we say that the first process will take a look at the flag, which if it's free, then it will set the flag to taken, right? And then enter the critical section. And everyone else would probably will be spinning on this flag, waiting for it to become free again, right? Agree with this? And that's pretty much a simple spin lock. So we can build it like this, right? So we say acquire spin lock data structure, we'll have a flag locked. So infinite loop, the moment it's unlocked, we set it to lock, break out of the loop, go enter the critical section. Agree?
No.
Don't agree. Okay. Well, clearly someone was in one of those classes which Okay, tell us what's wrong with this.
Because we could have multiple processors as doing the line 25. So all of them will come into the line 26. And then actually, in this case, this is not we expect. We expect only one thread could enter this section.
Correct. So look, see the problem, right? So multiple CPUs can reach the line 25. They are reading this line, right? So the cache coherence protocol will happily give them the line in a shared state, right? Which contains this flag. Agree? Both of them will see, let's say, 0 here and say, look, cool. Yeah, we probably can proceed to line 26, right? Why not? And at this point, like one of them tries to write it. Of course, that one will win the race, upgrade from shared to exclusive, and then write one here, upgrade to modified. And the second CPU will get this cache line in the exclusive state and also will write one here, and then will both enter the critical section. Agree? So clearly, this is not the right way to build a log. Everyone agrees on that? It's kind of important to understand those details. So how can we fix this? Question. Correct. So at a high level, what you want to happen, you want these two lines to be executed atomically. When I say this, I mean that CPU which executes this check and upgrade to 1 should be like, there should be no gap between the check and upgrade to 1. It's either you see 0, upgrade to 1, or if you try to do that almost instantly on another CPU, you will see 1, right? And okay, so CPUs came up with these special instructions, which again, they're very limiting, those instructions. By the way, exchange, it's instruction which swaps a word in memory with the new value. So you have a cache line, it has some value, let's say 0, you say exchange with 1, and it returns back the old value 0. So it like atomically, like in a single instruction, puts 1 here and returns the old value, right? So if two CPUs execute the same instruction exchange, only one of them will see 0, right? And the cache coherence will choose a winner. And exchange instruction itself on x86 is actually not atomic. It can be, okay, why it's not atomic? You say that's literally like just a single instruction. How on earth it can be not atomic, right? So does anyone know the answer to this? Correct. Inside, like it will do a load from a cache line from memory into some temporary register. We'll probably set this register, whatever, like to maybe, or we'll do a store like of another register into a cache line. And you can technically be preempted here because the cache coherence, you did a load, then started slowing down, maybe some interrupt arrived or something like that. And then another core says, okay, give me request for ownership, and this cache line, you lose it and it goes away and it is updated on another core.
So a CPU can execute this instruction.
Yeah. No, because internally it's multiple simpler instructions, kind of like a RISC architecture underneath, right? So again, I sometimes like an increment can be preempted, right? So like this x++, which translates to something like an increment instruction, can be not atomic, but because if it's on memory, it's internally like some loads and stores, right? So it sometimes counterintuitive, but on Intel, it's not atomic. But there is an atomic prefix. So Intel says, if you put a special prefix, we never seen it before, in front of this instruction, so what I was trying to spell here is lock, then I will actually lock this cache line for the duration of this sequence of instructions. Those instructions are very simple. It can only lock one cache line. So, and meaning a lock of a cache line, if this request for ownership comes from a different core, like remember when I was saying those requests come to a different to your core and you kind of give up this line, you will refuse to give up this line. The CPU says, okay, it's locked. I'm not going to give it back to you until it gets unlocked, right? And this is how this atomicity is implemented on Intel. So don't forget this lock, right? So lock prefix. So essentially, but if you simply rewrite this loop with this, its exchange function, you say it's atomically sets on and 1, and if it's returns 0, then you go out of the loop. If not, you will return 1 and it will keep spinning until someone resets it back to 0, right? But internally, you will have an exchange instruction with this lock prefix in front of it to make it actually atomic, right? Is that clear? So it's a little like there's like multiple levels of details here. Okay, and then of course, like then that it solves our problem, right? So at this point, you say, look, this is my spin lock.
So when you say it locks the cache line or the instructions?
At the level of hardware cache coherence protocol, it will refuse to give up this cache line to any other core. It will say it's mine. I will never reply to any messages from the cache coherence protocol until it gets unlocked by the pipeline. And so at some point, it's short, right? So it's not because those atomic exchange executes within like a couple of cycles, right? And so it's okay. It's a decent design choice. But it will not lose the cache line from its own local cache, right? There is a couple of, let me just quickly finish. There is a couple of things here. So it's actually a little bit more complicated than this, but everyone knows that CPUs reorder instructions, right? Yeah. Again, when you get to your interview, right? Just give me a sec. It's kind of important. CPUs execute instructions out of order, right? It seems that this instruction, which execute the lock, and instruction which does this update, they're independent. Why not to reorder them, right? Because maybe this cache line is already in your own local cache, so it's ready to go. Like the CPU can execute this right into the cache line and execute it in front of this acquire. Agree with this? Wow, but that sucks big time because then your locking paradigm just goes to hell, right? Because you lock, but suddenly this update is still executed before you even locked it, right? But we understand that this may happen, right? Intel does a smart thing for you. On some architectures, you really explicitly have to prohibit reordering of loads and stores around a specific piece of code. Intel just does not reorder around this lock prefix. So when Intel sees the atomic lock prefix, it says, okay, most likely you're doing something funky. We're not going to reorder loads and stores around those instructions, right? Mm-hmm. Just 2 more seconds. However, we also know that compilers do reorder instructions, right? Yeah. Well, why not? Because compilers are so smart, they can figure out that those are independent, they can put them out of order. And so technically speaking, you have to put this label. It's a directive to the compiler to say, do not reorder around this label. Otherwise, it will just move out instructions out of this atomic section, critical section. I don't think I've seen much of this in practice because I think compilers are also smart enough to not reorder around lock, but I don't know the answers for sure. So go into the compiler class and maybe ask this question, why does it work? Right. And for other instructions, because acquire can be in line and stuff like that. Okay, so I'm done. Thank you. Sorry, I'm like late 5 minutes, but it was important to finish. We will continue with synchronization a little bit next time and start file systems. Thank you.